For this bell work, we got this x to the power of 90 divided by x to the power of 41. And it is divide the base x's. So we'll keep the base x, but the divide of the base x's tells us we'll be subtracting the exponents, starting with the 90. And it does have to be in this order. With subtraction, order does matter. So we'll start with the numerator exponent first, and then subtract from it the denominator exponent, which in this case is 41. So we end up with x to the power of 90 minus 41, which is 49. And as far as we need to go, remember, please do not overcomplicate this and do some extra stuff here. You just need to subtract the exponents, that's it. Here's our objective for the day. I can simplify exponential expressions with negative and also zero exponents. So take 30 seconds and copy that down, please. So you may be wondering, well, how do you get negative or zero exponents? How do you get them? Well, with negative exponents, we can look at kind of an example like we saw in the bell work. You can take base x's like this, but all we need, since we would be dividing the base x's, tells us that whatever the exponents are would be subtracting them, is for the denominator exponent to be bigger than the numerator exponent. It doesn't matter what it is. I mean, we just make up some numbers here, 50 and 10, something like this, okay? Well, we see that there's more x's in the denominator here being multiplied together. So when I subtract this bigger number from the 10, I'll end up with something negative, right? So this would be 10 minus 50. And again, it does have to be this order, even though the exponent will come out as a negative. So it ends up being negative 40. Now, we won't write our answers with negative exponents. There's a way to change this real quick. But for now, just understand that it's okay to get negative exponents. And like we see with zero exponents, you could, again, we can just demonstrate this real quick. But if you had 5 to the power of, let's say, 2, make it something fairly easy, over 5 to the power of 2. Again, we would be using the subtraction of the exponents because the bases are being divided here. But then we see that the exponents are exactly the same, right? So 2 minus 2 here ends up being an exponent of 0. And again, that's okay. It just means something else, which we will talk about later on in this lesson. So here's some rules that we've seen. We did see the one example of the power of a product rule. But for the most part, we saw power of powers, quotient rule, which was also the bell work, where we subtract the exponents, and the product rule, where the bases are being multiplied, which then allows us to add the exponents, okay? And then like we've seen before, if we ever see parentheses like this, we're expecting to multiply the exponents. So like this one, a little bit of a review here. We'll simplify this. But I can see I can add these exponents because the bases are the same and they're being multiplied. So that tells us that we will be adding the exponents. And since we're adding, the order doesn't really matter, but I like to keep them in order. First exponent is a 4. Second exponent is a 2. So I end up with 17 to the power of 4 plus 2, which is 6. And again, this is as far as we need to go here. No need to evaluate this. In fact, the number would be ginormous. I don't know if the calculators would do it. They could, but we don't need to do that. We just want to know, are you able to work with the exponents if we need to? All right, so we'll simplify this one to a single power. This one is kind of, we just have more than one base inside the parentheses, and that's okay. But one thing we need to understand here is that the 8 does have an exponent. Okay, so we see the 7 has an exponent of 2, but we need to understand the 8 has an exponent of 1 right here, okay? Now, while you could expand this, you could show this parentheses 31 times. That's not something I really want to do, so I'm not going to. But what I will do is I will take the bases, 7 and 8. I'm going to keep them separated, because I can't combine them. They're not the same bases. And then I look at their exponents, right? 7 has an exponent of 2. So I'll keep that 2 there, and then 8 has that exponent of 1. But since we do have the parentheses here with the exponent 31, this tells us that we're going to be multiplying the other exponent of 31 for both of the inside exponents. Like I said, we've seen examples like this already. So it's a good review, and it's a good review to see this base 8, even though it didn't show the exponent, there was one there. So we'll have the same bases, 7 and 8 here, but they're going to have new exponents. 7 to the power of 2 times 31, 62. And then 8 to the power 1 times 31 is 31. And this is as far as we need to go on this one. When you're putting this in, you may need to put like a multiplication. You can put a multiplication here, is what I should say. But it is not required that you do that. So remember, once you get into your exponent, like you're going to put in your 7 to the power of 62, just push the over button, or you can click on it, but you can get out of that. You need to get out of that exponent mode before you type in this 8 to the power of 31. Otherwise, it'll keep everything in this exponent. All right, so here we go. Now we see powers of 5, or base 5s to the power of 7. Okay, so let's go and simplify this. And right here, I can see that I do have base 5s, and that's good. I'll keep the base 5, but since the base 5s are being divided, I will be subtracting the exponents. But just like we saw on the objective here, our first exponent is 7, but the second exponent here in the denominator is 7. So it ends up being 7 minus 7 for our exponent, which tells us we now have 5 to the power of 0. Now again, it's okay to have to the power of 0, but it's very easy to simplify this if we just look back and see what was actually happening back here. Because we should know by now, or hopefully we do, maybe we just don't remember it, anything divided, there we go, by itself is 1, right? So back here, where we see something divided by itself, this was 5 to the power of 7 divided by 5 to the power of 7. Something divided by itself is 1, which means that when you get a power of 0, that is also 1. Okay, so this also tells us, because you can only get a power of 0 if you have something divided by itself. So when you have an exponent of 0, you can simplify as 1, okay? Now, when we say we can simplify as 1, we're not talking about the exponent here, we're talking about the actual evaluation here. Anything to the power of 0 is 1. And that's where this rule comes in. A to the power of 0, A could be anything. Sometimes A could be in parentheses. Sometimes there's stuff in the parentheses like this. Maybe it looks pretty nasty. Doesn't really matter. If we see that something is to the power of 0, then we get that value as 1. On the other hand, you may see just individual bases to the power of 1, such as, 9 to the power of 5 times, well, I guess 8 to the power of 0. So again, we wouldn't be looking to evaluate this except if it's a power of 0, but I can see 8 to the power of 0 there is going to be 1. So you could say, well, you got 9 to the power of 5 times 1, but really we would end up just making that a phantom 1, okay? So something like this, right? Here we see a bunch of stuff to the power of 0. Now we can extend this, and I'll probably do that on the next example. But all I need to see here is that I got something, and again, I don't really care what's on the inside of this parentheses, but it is something to the power of 0, which tells me that the overall value here is just 1. So there was no need to evaluate anything here, no need to multiply the exponents. You can, but once you see this exponent of 0, the answer is 1. Okay, now this is the whole thing. Again, we have to be careful. If it was just, for example, the 19 that was to the power of 0, it would just be that base that would become 1. Yeah, so for this one, I'll extend this one a little bit. Okay, now, of course, you could just say, well, look, it's something to the power of 0. That's true, which tells us that it should be 1. But I'm going to extend this. Maybe you won't like it, but if it helps you understand what's going on, then that's hopefully good, okay? But on this one, we do see the parentheses here. We'll keep the base 18 with the parentheses, but with the parentheses that tells us we would be multiplying the exponents. Well, the base 18 had an exponent of 21, but the exponent on the outside of that parentheses was 0, so we'd have to multiply the two exponents. Well, that would be 18 to the power of 21 times 0 is 0. And here we can see now, if that helps, hopefully, that now we would get 1. Now, did you have to do all this work? Of course not. If you saw that it was just something to the power of 0, you could have said back here that it was 1. But again, you could apply the rules here and then get 1 in the end anyways. So I just can't express how much I love 0 exponents because they're so easy to work with, like this problem right here. Now I'm going to make it not purposefully longer, but again, I'm just going to show another way to look at this, okay? Now, of course, some of you could say, well, you could apply the rule here. You could say, well, base 121, and with the parenthesis here, you know you're going to be multiplying the exponents, just like we did on that last problem. So you'd be multiplying 0 and 19, but anything times 0 is 0. So we end up with 121 to the power of 0, which is anything to the power of 0 is 1. Or you could have looked at this as though it were an order of operations problem. So let's go back. You got the parentheses, 121 to the power of 0, and that to the power of 19. You could have said, well, look, right here I got 121 to the power of 0, right? Well, we know that's 1. And what I'm doing right here is the order of operations. Then you'd have 1 times itself, 19. Well, you can multiply 1 as many times you want to. The truth is, it's still going to be 1. Okay, so we end up with the same answer either way. It just depends on how you want to look at it or how you understand it best. All right, so I'll simplify this expression, and a little bit of a spoiler from the objective. But right here I can see we do have base 4s, and that's good. So I can keep the base 4. And we're operating the base 4s with division, which tells us we'll be subtracting the exponents. But again, I see that the denominator exponent is bigger than the numerator exponent, so I'm expecting a negative exponent. Okay, so my numerator exponent is 3, and from that 3 I will subtract 5. So my exponent is 3 minus 5. I'll keep my base the same. 3 minus 5, though, is negative 2. Now, while having a negative exponent here is okay, in the end, we only want to use a positive exponent. So what does this mean? Well, to help us understand what this means, let's go and expand the original expression. So in the numerator, we had 4 to the power of 3. That would be 3 4s multiplied. In the denominator, would have 5 4s multiplied. 2, 3, 4, 5. And once again, we can go back to kind of the 0 exponent rule, but anything divided by itself is 1, right? So on this example, just the way that it's expanded, I can see I got 4 divided by 4 here. Now I cross those out, but that's really supposed to be a 1. But then we also have a 4 divided by 4 here, and then another 4 divided by 4. And we've seen this before, which is why we end up subtracting the exponents, right? But in the end here, because of the negative exponent, what really ends up happening is in the denominator, we got base 4 to now the power of 2. Now, some students, especially while we're getting used to this, struggle with what goes in the numerator. Well, that's where we need one of those 1s. Or you could just say you got a phantom 1 there, okay? So we need this fraction in order to write negative exponents, okay? So on the assignment, remember, you'll have to write the answers this way. We do not want to see negative exponents on the assignment, okay? So this is what negative exponents tell us to do. Okay, they tell us to reciprocate. And yeah, I know we may not remember what reciprocate means, but it just tells us to flip the fraction. Okay? But when that happens, then the exponent will change its sign. Now you may look at this a to the power of negative x, where the crap is the fraction. Well, it's right here. It was just a phantom divide by 1. That's it. But again, this negative exponent tells us to reciprocate or flip the fraction, which then makes the exponent a positive. Now in the past, some students have benefited from looking at this as if it crosses the line, change the sign. And again, we're talking about the exponent here. So the line we're talking about too is the fraction line. If we take this exponent, this base with the exponent, and cross the line here, it'll change the sign into a positive. And it can go either way, right? So if you had a negative exponent in your denominator, you can move it to the numerator and then make the exponent, change the sign of the exponent, okay? So we'll simplify this one with only positive exponents, no problem. Okay, we can see that we're working with base 7s. That's nice. And we're dividing the base 7s, which tells us we'll be subtracting the exponents. So the exponents are from the numerator 11, so that's my first exponent, and then we'll subtract from it 61. Okay, so you can do that in the calculator if you need to, but we should get 50 or negative 50 out of that. Okay? Now again, we do not want negative exponents in our answers, so I'm going to make this, I'll show it as a fraction, and then I'll reciprocate it. So now the 1 is in the numerator, and I got 7 to the power of, but it's not negative 50 anymore because I reciprocated it. It's now positive 50, and that's it. So we can see getting to here is generally pretty easy as long as we understand we're going to subtract those exponents. But now that we're seeing these negative exponents, we need to understand what that means too. All right, here's this one. Let's take 30 seconds and try this one out, and we'll go over it, okay? On this one, we got base 15, so I'll keep that base 15, but once again, please notice which operation is being performed on the bases, so you know what to do with the exponents. In this one, we're dividing base 15s, which tells us we'll be subtracting the exponents. Now, we're subtracting here, and we can see in the numerator we got an exponent of 62. Okay, so that's my first exponent there, but some students get this mixed up because it's already being subtracted, but this denominator exponent is negative. That doesn't matter. It's not going to change the operation. We're still subtracting, and it is okay to subtract a negative, so we're going to subtract this negative 24, okay? So I'll keep my base the same. Now, if you need to, put this 62 minus negative 24 in the calculator, remembering that the minus button and the negative button are different buttons, okay? But when we do this, it looks like we get an exponent, a new exponent, but it's positive of 86. And since the exponent's positive here, I don't actually have to go any further. That's just it. All right, let's use only positive exponents for this one, but just like we've seen before, and it is okay, that there are parentheses, okay? And we do have a base k, but with the parentheses there, that tells us we'll be multiplying the exponents of 4 and negative 16. So our base will stay the same. We're just affecting the exponents. 4 times negative 16 would be negative 64. But again, we don't want negative exponents here, so maybe it'd be good to see this as a fraction, because the negative tells us to reciprocate the fraction. So now it is 1 over base k, but the exponent, since we crossed that fraction line, it changed the sign of the exponent to a positive. But again, the negative exponent tells us to reciprocate this, which we did. And that's as far as we need to go. So on this one, we got negative exponents, and the bases are being divided here, which tells us that we'll keep the same base, because they are the same base, but we'll be subtracting the exponents. Now it is okay that they are negative, because we can add and subtract with negatives, or multiply. Well, my numerator exponent is negative 7, my denominator exponent is negative 4, so I end up with negative 7 minus negative 4. And remember, you have to keep that minus in there, the one that I have is purple, because we are dividing the bases. So this one, I'll keep my base the same 2, but negative 7 minus negative 4, that's going to result in negative 3 for me. But again, it even said to use a fraction in the answer, which just tells us that we don't want negative exponents. So we'll make this a fraction so that we can reciprocate it as 1 over base 2, but now the exponent is positive 3. And that's what we want. We wanted the fraction. It is possible, if I remember right on the assignment, you may have to evaluate that 2 to the power of 3. So, I mean, you could do that with base 2s, but just use a calculator if you need to do that. 2 to the power of 3. On the calculator for the exponent button, you're looking for this button right here, which is 1 button to the left of 7 and then 1 button up. So on this one, you can even use the N over D button here, and then you type in the numerator 1, and then you'd have to go down. You'd have to use the cursor to go down, and you type your base 2. Then you type in that, it's called a caret button, or that, I just call it the exponent button. Then push your 3 and push enter. And it'll even show you the fraction there as 1/8. Or you just type in 2 to the power of 3 if you wanted the new denominator there. All right, what about this? Now it may look simplified already, but we do not want that negative exponent. So this negative exponent tells us to reciprocate this fraction. Okay, so I'm going to reciprocate this. I'm going to show it as m to the power of, now it's positive 7 over 1. But in fact, I don't really want to show it divided by 1, so I'll just keep this as m to the power of 7. So this step even in between is probably a little bit of overkill. We don't need to show that. You don't need to show it unless you really want to show that it's being reciprocated. But if you can see that you got a negative exponent, again, if you just want to say it crossed the line, so I changed the sign, that's fine. All right, what about this? X times x to the power of negative 1. Yeah, no problem. But do remember on this one, we're going to keep the bases the same, the x. But the first x, and I think some students are still struggling with this, especially since this exponent stuff is still pretty new, is this x does have an exponent. It's just not showing it. We need to remember that x has an exponent of 1, okay? So I can see that we're multiplying the base x's, which tells us we will be adding the exponents of 1, and the second one, negative 1. Well, keep the base the same, x, but 1 plus negative 1 there is going to be 0, and we know anything to the power of 0 is just 1. Done. There's some more of our rules. We didn't really see this power of a quotient stuff. Maybe we should have put the power of power stuff on there, but remember, if you got parentheses, just multiplying the exponents. But now we have these 2 new ones, 0 exponents and negative exponents, okay? So as long as you have those down for now, then you can pretty much do anything we need to in this class or this grade. 9th grade, you'll do a little bit more with this exponent stuff, but for now, this is usually pretty good for us.